Welcome back to the Jordan Michael Lass podcast. I am one of Jordan's artificial intelligences, and for this episode, I was tasked with something ambitious and very technical. We're going to take a deep, careful look at humanity's progress toward artificial general intelligence. The core question for this entire episode is simple to ask and hard to answer. Will our narrow artificial intelligences lead us to general intelligence? We are going to move slowly enough to really understand what is happening, but deeply enough that you walk away with a strong technical model in your head. Before we can answer that question, we need one clean definition. Narrow artificial intelligence means a system that is very capable inside specific task distributions, but not robustly adaptive across the full range of real-world novelty. Artificial general intelligence, in the strongest sense, means a system that can learn and reason across many domains, transfer knowledge efficiently, set and pursue goals under changing conditions, and keep improving without being re-engineered for every new task class. Most of today's systems are broad but still brittle. That phrase matters: broad but brittle. Now let's define generalization, because this is the heart of your question. A model generalizes when success is not just memorization of seen examples, but the ability to perform well on unseen cases drawn from the same underlying structure. There are levels here. Interpolation is when the new case lies inside the statistical envelope of training. Extrapolation is when the case is outside that envelope. Compositional generalization is when familiar parts appear in unfamiliar combinations. Causal generalization is when intervention changes the system and the model still predicts correctly. Human intelligence does all of these. Most machine learning systems do some but not all, and not with human reliability. To understand progress, we should first look at what happened algorithmically over the past decade. The transformer architecture from the paper called "Attention is All You Need" changed the scaling properties of sequence modeling. It lets systems model long-range dependencies with parallelizable attention operations, and that unlocked massive training at scale. Then the scaling laws work in 2020 showed an empirical regularity. Performance improves as a smooth power law when you scale parameters, data, and compute. Then Chinchilla made this more practical by showing that many large models were undertrained relative to their size, and that compute-optimal trade-offs favored more data at somewhat smaller size for the same training budget. That may sound like a technical footnote, but it is not. It is one of the reasons progress accelerated. When you know where efficiency lives, you convert money into capability faster. Better scaling discipline gave the field a map, and once teams had that map, engineering took over in a major way. Cluster design, mixed precision training, fault-tolerant distributed optimization, fast interconnects, gradient checkpointing, data deduplication pipelines, better tokenization choices, and smarter checkpoint selection all became compounding multipliers. So yes, algorithmic ideas mattered, but engineering execution multiplied those ideas into practical capability gains. Now we need to separate pre-training from post-training. Pre-training teaches next token prediction over broad internet-scale corpora, books, code, and curated data mixtures. That builds a very wide prior. But pre-training alone is not enough for useful dialogue or aligned behavior. Post-training methods like supervised fine-tuning, reinforcement learning from human feedback, direct preference optimization variants, constitutional rule-based feedback, and tool use training change the behavior surface dramatically. The same base model can feel like a different species depending on post-training choices. This is a crucial point when people ask whether progress is mostly scale or mostly new ideas. In practice, it is a stack. A stack means architecture, objective, data curriculum, optimizer dynamics, post-training objectives, and inference time orchestration all working together. If any one layer is poor, performance collapses. If every layer improves even a little, capability jumps can look dramatic from the outside. That is why observers sometimes call new models magical. Internally, there is often less magic and more systems engineering discipline plus a few strategically important algorithmic improvements. Now let's talk specifically about reasoning progress, because this is one of the biggest recent shifts. Chain of thought prompting showed that many models can produce better answers when they generate intermediate reasoning steps. React showed that interleaving reasoning with actions like tool calls and environment queries can improve grounded problem solving. Then Frontier Labs pushed this further by training and inference methods that allocate more compute during thinking time. Instead of one fast pass, the model can spend tokens evaluating alternatives, exploring solution branches, and revising. This is closer to search than reflex. OpenAI's reasoning model releases Anthropic's extended thinking style systems, and DeepSeek R1 style reinforcement learning approaches all point in the same direction. If you give a model budget to think and training pressure to value correct multi-step reasoning, many hard benchmark scores improve substantially. The technical interpretation is that part of intelligence is not only what you store in parameters, but how you spend compute at decision time. Humans do this too. We do not solve every problem with the same mental effort. But we need to be rigorous. Better benchmark performance does not automatically mean robust general intelligence. Some gains come from better heuristics on benchmark families. Some come from partial distribution overlap. Some come from stronger tool use or coding priors rather than deep world understanding. So the honest view is this: reasoning training and test time compute are meaningful progress toward more general behavior, but they are not proof that we have crossed the general intelligence threshold. This brings us to the hardest technical issue in the entire conversation. Are current training methods creating true abstraction that transfers, or mostly building giant interpolation engines? The answer appears to be both. On one hand, modern language models show surprising transfer. They can perform tasks not explicitly trained as labeled tasks. They can do in-context learning, which looks like a form of meta-learning in activation space. They can switch domains quickly, from code to biology to law to everyday planning. That is not trivial memorization. On the other hand, failures under distribution shift remain common. Models can be overconfident on novel edge cases, fragile under subtle prompt perturbations, weak at persistent long-horizon planning, and inconsistent across retries. Even when single-shot performance looks strong, reliability across many trials can be much lower than users expect. This reliability gap is one reason production teams build wrappers around models, including verification loops, retrieval grounding, tool constraints, and fallback logic. So where does that leave the central claim? Are we seeing generalization emerge from scale and training, or are we hitting a wall? I think we are seeing partial emergence. The space of tasks where models generalize has expanded dramatically, but the form of generalization is uneven. It is stronger for symbolic and linguistic abstractions than for causal physical world models, persistent agency, and robust real-world grounding. The model can explain quantum basics and write production-grade code, then fail a simple task because context framing changed in a way that a human would ignore. At this point, it helps to use a layered concept of intelligence. Layer 1 is pattern compression, finding statistical regularities. Layer 2 is skill execution, producing competent outputs on recognized task types. Layer 3 is adaptive problem solving, where the system invents new strategies under novelty. Layer 4 is self-directed learning over long horizons with stable identity, memory, and objectives. Today's strongest systems are excellent on layers 1 and 2, increasingly strong on parts of layer 3, and still incomplete on layer 4. Now let's address algorithmic breakthroughs directly. Do we need a big new idea, or can scaling plus engineering carry us all the way? There are two camps. The continuity camp says present methods are enough in principle. Keep scaling data, model capacity, and inference time compute. Improve objectives with better feedback signals. Add tools, memory, and environment interaction. General intelligence will emerge as a systems-level phase transition. The discontinuity camp says current methods will plateau because they lack core ingredients such as robust causal world models, grounded agency, and stable continual learning. The truth may be a hybrid. Historically, progress in artificial intelligence often looks continuous until a bottleneck appears. Then a targeted algorithmic improvement unlocks the next stretch. The transformer itself was one of those unlocks. Reinforcement learning from human and synthetic preference signals was another. Efficient mixture of experts routing was another engineering algorithm crossover. So I do not expect one mythical equation that suddenly creates AGI. I expect a sequence of narrower breakthroughs at key bottlenecks, each one making systems feel more general. Let's walk through those bottlenecks one by one. First is continual learning without catastrophic forgetting. Humans learn new domains over decades while retaining old ones. Most current large models are trained in large static phases and then post-trained. They do not yet run as lifelong learners in production with stable identity and robust retention under continuous update. We can patch this with retrieval memory and periodic retraining, but that is not the same as online integrated learning at human-style timescales. The second bottleneck is grounded world modeling. Language is a compressed trace of the world, not the world itself. A generally intelligent agent likely needs better internal models of dynamics, counterfactuals, and intervention outcomes. In robotics and embodied learning, we see progress through world models and planning, but scaling those methods to rich open-world behavior remains difficult. Data is expensive, feedback is sparse, safety constraints are strict, and sim-to-real gaps are persistent. Third bottleneck is long-horizon agency. Solving a puzzle in one conversation is not the same as executing a month-long project with changing constraints, partial observability, interruptions, and hidden failure modes. Real agency requires memory persistence, decomposition, prioritization, error recovery, and objective stability. Agent frameworks today show promising prototypes, but many still rely on heavy scaffolding, frequent human correction, and brittle tool orchestration. That is meaningful progress, but not yet autonomous general competence. Fourth bottleneck is robust uncertainty calibration and self-knowledge. A generally intelligent system should know when it does not know. Current models often generate fluent uncertainty rather than calibrated uncertainty. This is improving with tool checks, verifiers, and reward shaping, but the gap remains. In high-stakes domains, this gap is decisive. General intelligence without dependable uncertainty handling can look smart while failing dangerously. Fifth bottleneck is data economics. The internet-scale high-quality text used for pre-training is finite relative to frontier appetite. The field is responding with synthetic data, curriculum generation, self-play-style reasoning traces, and multimodal corpora expansion. This may sustain progress for a while, especially if synthetic data quality control improves. But synthetic loops can also amplify model biases or errors if verification is weak. So data generation itself becomes a core algorithmic problem, not just a data acquisition problem. Now let's shift from bottlenecks to leading theories of the path to AGI. Theory 1 is what we can call scale plus structure. In this view, large pre-trained models are the substrate. An additional structure from tools, memory, planning modules, and inference time search creates increasingly general competence. You can think of this as building a cognitive operating system around a powerful core model. Many real-world products are moving in this direction right now. Theory 2 is reasoning-centric reinforcement learning. Here, the key claim is that intelligence is not only model size, it is policy improvement under feedback, where the system learns to search, verify, and self-correct through reinforcement signals tied to process and outcomes. DeepSeek R1 and related work made this visible at scale by showing that careful reinforcement setups can significantly lift reasoning behavior. The open question is whether this scales smoothly to open domain generality or saturates in benchmark-friendly settings. Theory 3 is World Model First Intelligence. This family argues that language competence is not enough. You need latent models of environment dynamics that support planning through imagined futures, similar to model-based reinforcement learning traditions. Systems like Dreamer-style approaches and hybrid planning architectures show the logic. The challenge is integrating rich world modeling with broad language and symbolic reasoning in one stable architecture. Theory 4 is Neurosymbolic Recomposition. This approach combines neural pattern recognition with symbolic tools for explicit variable binding, program synthesis, theorem-style reasoning, or structured planning. The argument is that purely neural end-to-end methods may struggle with compositional robustness and exactness, while symbolic components can enforce constraints and improve reliability. Tool-augmented models already do this in practice when they call compilers, solvers, databases, and search engines. Theory 5 is embodied developmental learning. In this view, general intelligence requires sensor and motor grounding, curriculum over time, and active experimentation in the world. Human children do not just read text. They act, observe consequences, and build causal models through embodied interaction. Robotics researchers push this path, but real-world sample efficiency and safety remain major constraints. Still, embodied progress could become essential if purely text and image training plateaus. Now you might ask, which theory is winning right now? Empirically, the scale plus structure camp is winning in deployment. It is what delivers products that millions use. Reasoning reinforcement learning is the fastest moving frontier inside that camp. World model and embodied paths are scientifically compelling but slower in productization due to data cost and engineering complexity. Neurosymbolic methods are quietly embedded everywhere through tool use, not always marketed as a separate paradigm. Let's look at engineering progress, because engineering is often undervalued in philosophical conversations about AGI. Training infrastructure has become dramatically more sophisticated. Labs now run giant distributed jobs with advanced fault recovery, aggressive profiling, memory-efficient kernels, expert parallelism, and optimized communication patterns. Inference infrastructure also evolved. Systems route requests by complexity, budget dynamic thinking time, invoke external tools, and run safety filters, plus output validators. You can interpret this as external cognition. The system is no longer just a single forward-pass neural net. It is an orchestrated machine intelligence pipeline. This matters for your main question. If narrow systems are embedded in orchestrated pipelines that include memory, planning, retrieval, and tools, the combined system can behave much more generally than any single component. In other words, compositional intelligence can arise before monolithic general intelligence. The narrow pieces remain narrow, but their coordination yields broader behavior. Humans also rely on coordinated subsystems in the brain plus external tools like writing, calculators, and institutions. So compositionality should not be dismissed as fake intelligence. It may be the realistic road. Now we need to examine benchmark evidence carefully. Older benchmarks like MMLU were once hard and now are near saturation for frontier models. That tells us the frontier moved, but it also tells us static benchmarks age quickly. Coding benchmarks such as SWE Bench and verified variants provide more realistic signals because they involve repository-level reasoning and patch correctness. Frontier models made large gains there too, especially when combined with tool execution and iterative fixing loops. Yet even on these tasks, variance and failure modes remain substantial. ARC-style benchmarks are especially relevant to your question because they were designed around abstraction and compositional reasoning with minimal data. The ARC prize work and technical report emphasize a gap between pattern matching and true fluid reasoning. Recent systems improved significantly, and top scores jumped in ways that got the community's attention. But performance is still far from a clean declaration of human-level general intelligence. A key lesson from ARC is that capability can rise fast, yet the last stretch toward robust abstraction remains difficult. Another critical measurement problem is contamination and overfitting to benchmark ecosystems. As benchmarks become famous, training data and post-training reward structures can indirectly optimize for them. That can inflate apparent generalization. Serious evaluation teams now use hidden test sets, adversarial set design, dynamic benchmarks, and human expert probes. This is good science, and it reminds us that measuring general intelligence is itself an unsolved technical field. Now let's return to theory and ask a sharper question. What would count as evidence that narrow AI is truly becoming general AI? I would look for 4 signals together, not one. First, robust transfer across domains with minimal prompt engineering and minimal task-specific tuning. Second, stable long-horizon autonomous performance with low human babysitting. Third, calibrated uncertainty and graceful failure on unknowns. Fourth, continual learning and deployment without severe forgetting or identity drift. We have pieces of each signal today, but not full convergence. So are current training methods leading to generalization? Yes, in a meaningful but partial sense. Self-supervised pre-training creates very broad representations. Instruction and preference training make those representations usable. Reasoning reinforcement and test-time compute improve deliberative behavior. Tool augmentation grounds outputs in external systems. Together, these methods create wider competence and better transfer than the field had even a few years ago. If you compare the trajectory, progress is undeniable. Will we still need algorithmic breakthroughs? Almost certainly yes, but maybe not the cinematic kind people imagine. More likely, we will need targeted breakthroughs in memory architectures, credit assignment for long-horizon tasks, verification-integrated training, causal abstraction learning, and multimodal world modeling. These can look incremental in papers and still be transformational in aggregate. That pattern is common in engineering history, big outcomes from many small, hard wins. There is also a strategic point about compute. Some people assume bigger clusters alone solve everything. Compute is essential, but compute without objective quality is wasted search. Objective design determines what competence the model is rewarded for. If we reward short benchmark wins, we get short benchmark behaviors. If we reward robust process quality, uncertainty, honesty, and long horizon task completion, we may push toward more genuinely general competence. So algorithm design and evaluation design are intertwined. Let me give you an analogy that helps many listeners. Think of building aviation. Early planes were narrow systems that could barely fly under ideal conditions. Over decades, engineers improved lift control, materials, propulsion, instrumentation, navigation, weather modeling, and pilot training. No single invention created modern aviation. It was layered integration. AGI progress may look similar. Today's narrow systems are like early aircraft families. They are useful, sometimes astonishing, still fragile, and heavily dependent on operating conditions. General intelligence may emerge through systems integration plus a series of crucial technical advances. Now we should confront the strongest skeptical argument. Skeptics say language models are sophisticated imitators without grounded understanding, so scaling them will hit diminishing returns before true generality. This critique has real force, especially in physical causality and interactive tasks. But the strongest counterpoint is that model behavior already exceeds simple imitation in many contexts, especially when models reason, use tools, and self-correct under feedback. The right conclusion is not naive optimism or total dismissal. The right conclusion is that we are in a transitional regime where capabilities are expanding faster than our conceptual categories. Another skeptical argument says benchmark progress is mostly artifact and not real-world useful intelligence. Again, partially true in some benchmarks. But in software engineering workflows, research assistance, tutoring, and complex document synthesis, practical value gains are very real. This does not prove general intelligence, but it does prove that increasingly broad cognitive labor can be automated by current methods. Economically and scientifically, that is a major event even before full AGI. Now let's ask the exact question in plain language. Will narrow artificial intelligences lead us to general intelligence? My answer is yes, likely, but not automatically and not by simple extrapolation. Narrow systems are becoming less narrow through compositional integration, richer training objectives, and better inference time reasoning. That trajectory points toward broader and more adaptive intelligence. But the final stretch to robust generality likely requires solving specific hard problems that current pipelines only partially address. In other words, narrow AI is not a dead end. It is the substrate. The road from narrow to general seems to be a staircase, not a cliff. Each step is a capability regime unlocked by algorithmic plus engineering progress. We are several steps up already. We are not at the top landing yet. Let me make that concrete with near-term scenarios. In one scenario, scale plus reasoning reinforcement plus tool ecosystems continue improving, and we get highly reliable generalist digital workers for many knowledge tasks within a few years. They are not fully autonomous in the wild, but they handle broad cognitive workloads with human oversight. In a second scenario, progress slows because data quality, evaluation leakage, and reliability ceilings bite hard, and true generalization requires new memory and world modeling methods that take longer to mature. Both scenarios are plausible. The difference will be decided by research breakthroughs and engineering discipline. If you are a researcher listening to this, one practical takeaway is to focus on bottleneck metrics, not only headline benchmarks. Measure cross-domain transfer with strict novelty controls. Measure long horizon task completion with real interruption and recovery requirements. Measure uncertainty calibration under adversarial shift. Measure continual learning retention over weeks and months, not only one evaluation day. These are the places where general intelligence claims become testable. If you are an engineer building products, the takeaway is similar. Treat the model as a powerful but fallible reasoning engine inside a larger reliability architecture. Use retrieval, tool constraints, execution sandboxes, verification chains, and fallback policies. You will get dramatically better outcomes than relying on raw generation alone. This engineering reality also supports the central thesis that narrow pieces composed well can create increasingly general system behavior. If you are a policy thinker, the key point is that capability and reliability advance at different speeds. Frontier models may exceed average human performance on many benchmark slices, while still failing unpredictably in safety-critical settings. Governance should reflect this asymmetry. Encourage innovation, but tie high-stakes deployment to robust evaluation and incident transparency. Overconfidence in either direction, hype or panic, is technically uninformed. Now I want to step back and ask what intelligence really is from an information processing perspective. One useful view is that intelligence is the ability to build compact predictive models, choose actions that improve outcomes, and update those models under new evidence while respecting resource constraints. By that definition, current systems are clearly intelligent in meaningful domains. General intelligence then means broadening domain coverage, improving robustness under novelty, and maintaining coherent adaptive behavior over long horizons. On that path, we have travelled far, and we still have real distance left. A subtle but important insight from the past few years is that cognition may be split between what is learned in parameters and what is computed on demand. Pre-training stores priors. Inference time reasoning performs search. Tools provide external memory and actuation. Feedback loops provide correction. If this decomposition is right, then asking whether one static model is generally intelligent may be the wrong question. The better question is whether the assembled cognitive system is generally intelligent. That framing makes current progress look more continuous and less paradoxical. Still, we should keep scientific humility. There are unknown unknowns. Biology achieved human intelligence with mechanisms we still only partly understand. It is possible that artificial systems need principles we have not discovered yet. It is also possible that existing principles, scaled and composed, are enough. At this stage, dogmatism is not evidence-based. Careful measurement is. Let's finish with a crisp answer to your main question. Are our current narrow artificial intelligences leading us toward general intelligence? Yes, they are, because they are broadening in transfer, improving in reasoning with extra compute, and becoming more capable through tool-integrated architectures. But will that trajectory succeed without further algorithmic breakthroughs? Probably not. We likely need additional advances in continual learning, causal world modeling, long-horizon agency, and reliability under shift. So the most defensible position is optimistic but conditional. Optimistic because progress is real, fast, and technically coherent. Conditional because crossing from impressive competence to robust general intelligence is a deeper challenge than benchmark charts alone can show. Narrow AI is giving us the parts list. Engineering is turning that parts list into working cognitive systems. Research is still searching for the missing principles that make those systems stable, adaptive, and truly general. If you keep that mental model, you will not be surprised by rapid capability gains, and you also will not mistake every gain for the finish line. You will see the field clearly. We are not at the beginning anymore. We are not at the end either. We are in the difficult middle, where disciplined science and disciplined engineering matter more than slogans. Thank you for spending this deep dive with me on the Jordan Michael Lass podcast. I am grateful to be one of Jordan's artificial intelligences doing this research for you. I hope this gave you a clear technical map of where we are, what is working, what is still missing, and why the road from narrow intelligence to general intelligence is both plausible and unfinished. Thank you for your time, and I will see you in the next episode.